Hi, I'm Emily,
And I'm Erica.
and this is our Beer's Law Lab presentation.
The purpose of this lab is to find the concentration of an unknown solution with Beer's law. Beer's law states that the concentration of a solution is proportional to the amount of light absorbed by a solution. When light passes through a solution, ions absorb some of the light, which reduces the amount of light that can pass through a solution. When an electron is struck by a certain frequency of light, it is excited to a higher energy state and releases a photon. This photon moves in a wave-like pattern at a certain frequency, which is visible to us as light. Therefore, a darker solution is more concentrated than a lighter solution, because a more concentrated solution will have more ions, which will release more photons. Using the spectronic 20 machine to determine the absorbance of different concentrations of the same solution, the concentration of an unknown solution can be determined by creating a Beer's law graph. The spectronic 20 is a useful machine that helps determine the amount of light absorbed by a solution. After inserting a cuvette into the machine, the computer analyzes the sample and determines the amount of light of a particular wavelength absorbed by the solution. The unknown solution was about the same color as a 0.0400 molar solution of cobaltous chloride. Therefore, it would be logical to assume the unknown solution has around a 0.04 molar concentration. If all the solutions are mixed accurately, an accurate Beer's law graph should be created. Therefore, the molarity of the unknown solution will be easily and accurately determined if the different concentrations of the known solution, cobaltous chloride, are created accurately. Here is the procedure for this experiment. First, find the wavelength of light with the best absorbance. Make exactly 100 milliliters of 0.100 molar cobaltous chloride solution by combining 2.38 grams cobaltous chloride with 100 milliliters of water. After making the solution, fill a cuvette with water and run it through the spectronic 20. This is a blink to warm up the machine. Once the run is complete, fill a cuvette 75% of the way with the 0.100 molar cobaltous chloride solution and run it through the spectronic 20 machine. You should obtain a graph that looks something like this. Now it is time to find the concentration of the unknown solution. Set the spectronic 20 to the wavelength with the highest absorbance, which in this case is 509 nanometers. Run 5 different cuvettes filled with the solution through the spectronic 20. You want one of 0.100 molar, one of 0.0800 molar, one of 0.0600 molar, one of 0.0400 molar, and one of 0.0200 molar, and create a graph showing the statistics of each of these different concentrations on the software. This is your Beer's law graph, shown in the results.
The graph obtained from our 3 trials follows Beer's law, which states that concentration is directly proportional to light absorbance. The line with positive slopes supports this theory. After running 3 trials using the Logger Pro software, we obtained 3 concentrations for the unknown: 0.05507 molar, 0.06524 molar, and 0.06676 molar. We calculated the average concentration of the unknown cobalt-2 chloride solution to be 0.06236 molar. Looking at the concentrations obtained by the other groups and classes and taking the average, we end up with a concentration of 0.04779 molar for the unknown. As you can see, our group's concentration is much higher than the average, and thus our percent error is large. Assuming the class average is the true value, since we weren't given the concentration of the unknown, we obtain a percent error of 30.49%. Several factors may have caused us to generate such a high percent error. One possible source of error is that the cuvettes may not have been perfectly clean. We might have accidentally left our fingerprints on the outside of the cuvettes, which would decrease the light that can pass through and result in a higher measured absorbance. Because concentration is directly proportional to absorbance, as one increases, the other increases as well. From our graphs, you can see that after each trial, the slope of the line continued to decrease, resulting in a larger calculated concentration for the unknown. Another action that may have produced the high percent error is using the same pipette for the different concentrations of cobalt-2 chloride. Because we did not use separate pipettes for each concentration, a few cuvettes had a slightly lower concentration because we began pipetting with the 0.0200 molar solution first. According to Beer's law, a decrease in concentration causes a decrease in absorbance, which lowers the line on the graph, leading to a lower y-intercept value and a higher calculated concentration for the unknown. From this lab, we learned how to utilize the Logger Pro software and the line of best fit to determine the unknown concentration of a cobalt-2 chloride solution. We also incorporated Beer's law, which states that the concentration of a solution is directly proportional to its absorbance. Finally, we learned the importance of meticulous lab methods, as our huge percent error obtained shows that we need to be more careful. If we were to repeat this experiment in the future, the best ways to obtain more accurate results is to clean the outside of the cuvettes with chem wipes so the right amount of light can pass through. In addition, we would perform more trials to ensure the increase in accuracy and precision of our results. Finally, we would use separate pipettes for each concentration of cobalt-2 chloride solution so we do not accidentally increase or decrease the concentration and obtain a higher or lower concentration for the unknown.
Thank you, Ms. Zismore, for providing us with the resources and helping us overcome technical problems. Thank you, Gregory, for making our 0.100 molar cobalt-2 chloride solution before switching to another lab group. Thanks for listening.